quantum-driven analysis has just unraveled the mystery surrounding 3E Atlas. According to the latest findings, this interstellar object isn't merely unusual. It exhibits the same type of unexplained behavior that left astronomers scratching their heads over ʻOumuamua in 2017. But this time, the stakes appear to be significantly higher. Data from quantum-enabled instruments didn't only capture strange motions. They also revealed a dangerous internal instability, suggesting that 3E Atlas could fragment as it barrels toward the upcoming solar maximum. Should pieces of an object racing at 60 kilometers per second cross paths with Earth's orbit, they could endanger satellites, disrupt power grids, and pose risks to aviation systems. The question now is, what does this breakthrough really signify? And are we standing on the edge of the first true collision between quantum physics and interstellar uncertainty? On July 1st, 2025, the Atlas telescope in Chile tracked a rapidly moving object slicing across the dense star fields near the center of the Milky Way. Astronomers confirmed only hours later that its trajectory was hyperbolic, approaching but not bound to the Sun. This visitor, labeled 3I/Atlas, is now the third verified interstellar traveler observed passing through our solar system. At the time of its detection, it was already racing at 61 kilometers per second, far faster than any asteroid in the main belt. To put it into perspective, that's nearly double Earth's own escape velocity, fast enough to break free from every significant gravitational anchor in the solar system. Atlas's autonomous scanning systems picked it up at a distance of 4.5 astronomical units from the Sun, where even Jupiter's influence is little more than a subtle tug. Early brightness measurements hinted at a large body, though it remained uncertain if the glow was from a solid core or gaseous emissions. Follow-up observations by the Hubble Space Telescope narrowed estimates of its nucleus to a range between 320 meters and 5.6 kilometers, with a stronger probability of being under a kilometer. That makes 3I/Atlas, at minimum, a mountain-sized chunk of rock and ice shielded by a haze of vapor, smaller than an urban center, but capable of crossing the Atlantic Ocean in under a minute. What truly separates it from other bodies is not only its hypervelocity or interstellar origin, but also the scale of its surrounding coma. Measuring about 24,000 kilometers across, nearly twice Earth's diameter, it dwarfs the compact nucleus that could easily fit within Manhattan. The consequences of these findings are profound. Every inbound object from another star system serves as a cosmic carrier, embedding secrets about the birth of planets and comets light years away. But 3I/Atlas is unlike the ones before it. Its unique speed, brilliance, and behavior have sparked a worldwide scientific hunt, with astronomers rushing to gather every possible data point before it completes its arc around the Sun and permanently departs. The next phase of the investigation focuses on the composition of its carbon-heavy coma and the chemical signatures that may reveal the history of its birthplace. The appearance of 3I/Atlas instantly drew comparisons to the mystery surrounding ʻOumuamua in 2017. That earlier interstellar interloper defied classification, breaking the very models astronomers relied on. Its trajectory was hyperbolic, confirming its arrival from deep space. But as it exited, something even stranger occurred. It appeared to accelerate under a force that could not be accounted for by solar gravity alone. Typically, comets speed up by expelling jets of gas when sunlight warms their icy surfaces. But ʻOumuamua showed no signs of such activity. No tail, no visible emissions, nothing but still. The motion shifted. The body's brightness patterns revealed even more oddities. As it rotated, its light fluctuated in a way that suggested an extreme, elongated structure, possibly 10 times longer than it was wide. This configuration was unlike anything documented in our solar neighborhood, more reminiscent of a stretched cigar or even a flat, disc-shaped shard than a conventional comet. Its reddish surface reflected light similar to organic-rich objects found in the Kuiper Belt. Yet the absence of dust or gas made it utterly enigmatic. No one could say with certainty if it was made of stone, metal, or something altogether unfamiliar. Hypotheses flooded in. Some imagined it as debris from a planet torn apart. Others speculated about alien engineering, a probe, a light sail, or a shard of matter shaped by forces we can't yet comprehend. Yet every theory stumbled on contradictions. If it was losing gas, why didn't its spin change? If sunlight was pushing it, how did its odd geometry explain that effect? And if it were nothing more than a rock, how did it arrive with such velocity and at such an unusual trajectory? What made ʻOumuamua unforgettable wasn't only its puzzling origin, but also its refusal to conform to any established category. With the instruments available, optical scopes, spectra, radar, the mystery remained unresolved. That uncertainty left a deep impression. If the very first known interstellar wanderer could behave so strangely, what other oddities might be sliding through, undetected or misinterpreted? Can our current observational methods identify the next anomaly before it vanishes? And if a new enigma appeared, would we even realize it in time? If you've got your own idea about ʻOumuamua's true nature, consider sharing it, because every new discovery only expands the possibilities. The game has changed thanks to quantum technologies, transforming how astronomers investigate bodies such as 3I/Atlas. Only a few years ago, observations meant pointing a telescope, measuring reflection, and waiting for clear skies. Today, the toolkit is sharper and stranger. Take NASA's Cold Atom Lab aboard the International Space Station. Launched in 2018, it cools atoms to fractions of a degree above absolute zero, harnessing their quantum wave properties to build the most sensitive motion detectors ever created. This technique, atom interferometry, allows researchers to detect delicate gravitational fluctuations and vibrations invisible to classical instruments. In microgravity, the method works for longer periods. The atoms drift unhindered for seconds, giving readings remarkably clean and precise. That's sensitive enough to notice the faint gravitational tug of a passing rock or subtle variations in a surrounding field. But the revolution isn't just hardware. Quantum-inspired algorithms are now mining vast telescope archives for patterns imperceptible to humans. Their strength lies in parallel analysis. Instead of testing one hypothesis at a time, they explore all correlations simultaneously, like spinning every coin in a jar in unison. This makes anomalies stand out before slipping below data noise. For interstellar candidates, such detection power is transformative. The same kind of analysis that uncovered gravitational waves at LIGO and mapped hidden dark matter filaments is now applied directly to comet dynamics, brightness variability, and chemical trails. The cold atom sensors are so sensitive they can register something as slight as a vibration across a space station beam or a minuscule distortion in the local gravity field. That means, in principle, even a subtle irregularity in the behavior or structure of a comet could be recorded, not through conventional imaging, but through the way the atoms themselves react. Coupled with quantum-enhanced data analysis, astronomers now can fuse orbital paths, photometric spikes, and spectroscopic details in real time, forming a layered profile of every cosmic visitor. If an acceleration occurs, if a composition seems anomalous, or if activity bursts unexpectedly, these systems don't merely notice, they measure it with cutting-edge precision. So, when 3I/Atlas arrived, the quantum arsenal was primed and ready. Every particle of light, every spectral line, every wobble in its movement was cataloged, cross-checked, and recalculated. The outcome: scientists aren't passively tracking an odd object flying past, they're deconstructing its every action, searching for traces of processes we've never recognized before. With quantum tracking in the mix, even tiny deviations prompt immediate international alerts. The next pressing question: what exactly did these instruments uncover in the case of 3I/Atlas? And how does it compare with ʻOumuamua's mystery? The James Webb Space Telescope provided one of the biggest surprises. Instead of water dictating the chemistry, carbon dioxide dominated the activity around 3I/Atlas. JWST's near-infrared spectrograph revealed the coma venting about 129 kilograms of carbon dioxide every second, while water vapor barely reached 6.6 kilograms per second. That's a CO2 to H2O ratio of 8:1, a full 6 standard deviations beyond what's considered normal, even among the strangest comets within the solar system. In most cases, comets at similar distances are water ice driven. with carbon dioxide playing a minor role. Here, the hierarchy is completely flipped. JWST's integral field unit divided the coma into 30 slices, and in every segment, the 4.3 micron CO2 band glared brighter than water's feeble signal. The carbon dioxide wasn't just present, it stretched outward, strongest in the sun-facing region, accompanied by a dust field suggesting ultrafine grains less than a micron wide. Water, by contrast, registered as only a faint marker near 2.7 microns, barely visible against the background. Additional species such as carbon monoxide and carbonyl sulfide were there too, though far less significant compared to the CO2 surge. This chemical imbalance tells a radical story, because carbon dioxide is more volatile than water ice. It starts sublimating at colder temperatures and greater solar distances. That means 3I/Atlas began expelling carbon dioxide long before its water stores warmed enough to escape. Imagine its surface as a crust-sealing deep deposits of frozen CO2, abruptly igniting after eons in interstellar darkness. As warming sunlight breached its shell, the pressure forced eruptions that carried dust and icy grains outward. Water ice remained dormant until it drew much nearer to the sun, giving the coma its unusual, carbon-heavy composition during approach. The numbers are unambiguous: 129 kilograms per second for CO2, 6.6 for H2O, 14 for CO, and 0.43 for OCS. Compare that to comets such as 67P/Churyumov-Gerasimenko, where water production outweighs carbon dioxide by orders of magnitude. Even the highly unusual comet C/2016 R2, famous for its volatile chemistry, doesn't match this skew at the same heliocentric distance. Adding one more twist, the spatial mapping shows that CO2 venting peaks exactly in the sunward regions, directly tied to areas of maximum solar heating, while water vapor remains diffused and weaker. This strongly hints that the surface contains carbon dioxide-rich pockets close to the exterior, able to erupt as soon as sunlight penetrates shallow layers. Fine dusting of water ice has been detected in the coma, but its scattering profile suggests it isn't being lifted by water vapor like in normal comets. Instead, the grains are being hurled out by bursts of carbon dioxide. What does that tell us? Chemically, 3I/Atlas stands apart. It may be the remnant of a colder, carbon-rich protoplanetary disk, or perhaps a survivor from a region where cosmic rays or stellar winds stripped away water long ago, leaving CO2 as the dominant volatile. Either explanation points toward a nucleus that is fragile, pressure-sensitive, and far less stable than any local comet we have cataloged. The critical question becomes, does this chemistry prime the nucleus for instability as it nears the sun? And what will happen if carbon dioxide jetting pushes the structure past its breaking point? Quantum detectors have already uncovered something no one expected: a tremor. The vibration was faint but continuous, pulsing through the nucleus like a slow heartbeat. Unlike deep seismic activity in a mountain-sized rock, these were delicate, subhertz oscillations, too subtle for classical instruments, but obvious to the atom interferometers monitoring it. The signal hints at a body riddled with voids, more porous drift than solid stone. The rhythm repeated just under 1 cycle per second, strongly pointing to a composition closer to a loose snowpack. Density modeling backs this view. Calculations combining interferometer readings and coma mass suggest a bulk density under 0.4 g per cubic centimeter. That makes 3I/Atlas lighter even than Cork, and lower than 67P/Churyumov-Gerasimenko, the most famously fragile comet in the Inner System, which measures around 0.47 g/cm superscript 3. The data implies that 3I/Atlas is mostly open space, held together by frozen volatiles and weak surface cohesion. Atom interferometers don't just track motion, they also sense shifting stress. Every outburst of gas from 3I/Atlas leaves its mark, sending tiny recoils through its core. These microquakes consistently cluster near active regions where CO2 activity is strongest. Each venting event leaves a fingerprint in the quantum data, a record of the pressure buildup and its sudden release as another gas pocket finds a crack to escape. Similar patterns appear in lab experiments with porous matrices loaded with volatile ices, even slight heating triggers cascading fractures, breaking the structure apart. All of this builds toward the same conclusion: the comet's internal framework is brittle. Its low density and hollowed texture make it prone to collapse under stress. As increased sunlight warms its nucleus, the faint vibrations could multiply, potentially escalating into total fragmentation. The quantum measurements present a clear warning, repeating subhertz tremors, a density below 0.4, and a body that behaves more like frozen foam than a compact rocky core. Just one strong jet eruption or a sharp thermal shift could send the fragile lattice unraveling. Moving closer to the sun means more pressure, more venting, and more chances for catastrophic failure. Survival becomes a question of resilience, and time is running thin. Overlay this with the broader backdrop. Solar cycle 25 is already hitting intensity levels beyond forecasts. In October 2024, the monthly sunspot count spiked to an average of 160.8. Each sunspot represents twisted magnetic fields compacted with energy, ready to snap into violent release. When they erupt, the sun hurls out solar flares and coronal mass ejections, CMEs, that rip through the solar system. Some of these CMEs have reached speeds over 500 kilometers per second, more than 4 times the sound speed in the sun's outer plasma. In May 2023, the sun averaged 6.1 CMEs per day, the highest frequency ever recorded, the most extreme yet. An X9.0 flare on October 3, 2024, emitted so much radiation it overloaded detectors on several satellites almost instantly. Such events are not cosmetic. They are collisions of plasma and energy traveling at extreme speeds. The continuous solar wind itself, a flow of protons and electrons, surges during these solar peaks, turning interplanetary space into a turbulent corridor of pressure and charge. By October, the geomagnetic activity index reached 13.41 nanotesla, levels capable of blacking out grids, disrupting GPS, and forcing spacecraft to shut down systems. And this is the volatile environment that 3I/Atlas is now plunging into. Its orbit steers it straight into the heart of solar maximum. At the very moment the sun is most violent, every CME, every shock front, is a possible collision with a plasma wall racing at hundreds to thousands of kilometers per second. For 3I/Atlas, these encounters aren't just celestial fireworks, they are survival tests against an environment that could finally push its fragile shell beyond endurance. Solar storms have the power to strip away a comet's surface layers, trigger sudden surges in outgassing, or fracture its crust as temperatures and magnetic fields swing violently. The data makes this clear. During the last major geomagnetic storm, the solar wind near Earth doubled in density, while its temperature spiked to 4 times the norm. Even farther out, past Mars's orbit, these upheavals still retain significant strength. For a body like 3I/Atlas, fragile, riddled with cavities, and saturated with volatile ices, every uptick in solar wind becomes a fresh stress test. Its carbon dioxide-dominated chemistry makes it especially unstable. Unlike water-rich comets, 3I/Atlas begins venting gas at much lower temperatures. This means even a modest pulse of solar energy or an increase in charged particles can ignite jets that blast material outward. The pressure doesn't come from heating alone. Charged particles from a coronal mass ejection, CME, can penetrate beneath the surface, warming concealed deposits of CO2 and forcing pressure spikes from within. Shifting magnetic field lines can also wrap around the nucleus, inducing electric currents that trigger microcracks or possibly larger collapses. Under these conditions, the sun is far from passive. It becomes an active engine of disruption, bombarding 3I/Atlas with plasma, particles, and heat from every direction. The next CME could be enough to destabilize a vulnerable region and spark a failure cascade. And as the comet plunges closer to the sun, that likelihood only increases. Solar maximum ensures that time is not on its side. Powerful events are arriving at rates unseen in decades. The stage is now set for a dramatic confrontation between an interstellar fragment of ice and dust and the full destructive force of our star. Every cometary breakup begins with a flaw. For 3I/Atlas. That flaw defines its very makeup, a lightweight nucleus riddled with voids, saturated with CO2, and barely bound together by weak structures. Data from Hubble and JWST present the stark truth. A core no larger than Manhattan is shedding 129 kilograms of carbon dioxide every second, while its water vapor production is only a fraction of that. This bizarrely skewed ratio is more than unusual. It's a warning flag, because CO2 sublimates at much colder temperatures than water. Mounting internal pressure develops in 3I/Atlas long before the Sun gets close enough to trigger typical cometary fireworks. Now add in today's solar climate. Cycle 25 is raging. Sunspot counts peaked around 160. X-class flares are recurrent, and CME activity has reached record highs. Each CME is essentially a rolling wall of plasma traveling at speeds exceeding 500 kilometers per second. When such an event collides with a porous, brittle comet nucleus, the damage reaches deep below its surface. Radiation and charged particles infiltrate the crust, heating buried ices and generating sudden internal stress. In effect, it's like inflating a balloon made of fragile dust and frozen foam, then blasting it with a heat lamp. Modeling fragmentation scenarios reinforces the risk. Assume a nucleus with density under 0.4 g/cm superscript 3, lighter than cork, loosely held together. Inject extra pressure from outgassing jets. Strike it with a solar storm. The result isn't gradual erosion, but runaway collapse. Microfractures radiate outward, cavities implode, and slabs of the comet shear away, each carrying volatile reservoirs of their own. History provides precedent. In 1992, Jupiter's tidal force tore the comet Shoemaker-Levy 9 into more than 20 pieces that later crashed into the gas giant with energies that scarred its atmosphere larger than Earth itself. For 3I/Atlas, the tearing agent isn't a planet's gravity, but the fierce output of the Sun. Simulations warn that if a CME or solar wind spike coincides with peak CO2 venting, the nucleus could fragment suddenly. Pieces would continue along the original hyperbolic trajectory at various velocities, ranging from tens of meters per second to several kilometers per second. Some shards could be no larger than houses, others rivaling the core's original mass, with an inbound velocity over 60 kilometers per second. Every fragment transforms into a high-speed projectile that could sweep across the orbital plane of the inner planets or streak outward into interplanetary space. Time, however, is pressing. The deeper 3I/Atlas moves into solar maximum, the greater the odds that one internal weakness gives way. A fracture could spawn a debris train along its orbit, with some fragments potentially intersecting Earth's path or threatening spacecraft across the inner solar system. This isn't speculation. Every recorded cometary breakup leaves debris in its wake, some benign, others devastating. The distinction for 3I/Atlas lies in its velocity, composition, and timing. If you want to understand how such a cascade might affect satellites, navigation systems, and planetary defense efforts, now is the time to pay attention, because in this contest, satellites and infrastructure don't get retries. Once a solar storm strikes, survival depends on preparation alone. The numbers speak for themselves. In February 2022, one geomagnetic storm destroyed 40 newly deployed Starlink satellites within hours. None achieved operational orbit. SpaceX watched helplessly as solar activity drove atmospheric density higher, increasing drag until each craft re-entered and burned up over the Atlantic, nearly $20 million erased in a single event. And that incident wasn't unique. During the May 2024 Gannon storm, precision GPS farming equipment in the American Midwest malfunctioned, while commercial aircraft struggled with lost navigation signals for hours. That same storm also generated temporary radiation belts around Earth that persisted for weeks, threatening every vehicle in low orbit. Capella Space lost 2 satellites outright after Earth's atmosphere swelled beyond forecast levels due to heating from solar energy. NOAA's models had underestimated conditions, leaving the craft unable to recover. The hazard extends far beyond orbit. On March 13, 1989, a coronal mass ejection struck Earth's magnetosphere, Within 2 minutes, Hydro-Quebec's grid collapsed, 6 million people plunged into darkness. New York and New England lost more than 500 megawatts as transformers overheated and tripped offline. Though the blackout lasted only 9 hours, its financial shockwaves lasted much longer. Today's power networks are even more complex, interconnected, and dependent on satellite-driven inputs. Ironically, those same satellites remain vulnerable to the storms that threaten the grids on Earth, and the risk curve is climbing. Solar Cycle 25 is already producing unprecedented measures: higher sunspot counts, more CMEs, greater geomagnetic disturbances. Yet most commercial satellites were designed for average space weather, not extremes. The Gannon storm underscored that even updated models can be wrong by a factor of 3. By the time anomalies are detected, spacecraft often cannot maneuver or shield effectively. They are sitting targets. Aviation isn't spared either. Under high solar particle flux, radio contact at polar routes often fails. Airlines are forced to reroute, adding to costs in time and fuel. In May 2024, U.S. flight cancellations spiked from 1% to nearly 6% as navigation and communication systems were disrupted. Such failures cascaded through passenger schedules, freight movement, and emergency responses simultaneously. Quantum-equipped instruments and advanced predictive models are beginning to cut anomaly detection time. But the effective warning space remains dangerously narrow. NOAA's SCAVA probe at the L1 point provides anywhere from 15 to 60 minutes of notice before a massive storm arrives. That is barely long enough to shift satellites into safe mode or reconfigure grid operators. Add in the prospect of 3I/Atlas if fragments intersect Earth's orbit during a solar maximum. The outcome could be devastating. A meteoroid swarm moving at tens of kilometers per second would shred through satellites, GPS constellations, and potentially key defense assets. The vulnerability is stark. Our interconnected systems, spacecraft, grids, avionics, are fragile to sudden space weather shocks. A single solar storm can simultaneously cripple satellites, disrupt flight operations, and cause widespread energy outages. There's no redundant grid in space, and each solar maximum ratchets up the baseline hazard. The real uncertainty is not if a storm will strike, but whether our infrastructure can handle the aftermath. And with 3I/Atlas plowing toward perihelion during the most powerful solar cycle in decades, the margin for safety grows thinner every day. The looming question isn't whether another anomaly will test the global network, but whether it will arrive when we are least prepared. Planetary defense celebrated its most visible success in September 2022, when NASA's DART mission slammed into Dimorphos. The 570-kilogram spacecraft struck at 530 kilometers per hour, delivering enough momentum to alter the asteroid's orbit by 32 minutes. The impact kicked immense volumes of material into space, multiplying the effective force by a factor of 3. For the first time, humans proved they could actively redirect a small asteroid rather than just observe its trajectory. Yet, DART also exposed the fragile limitations of existing defense strategies. The test targeted a binary asteroid under 200 meters wide, orbiting a parent body only 11 million kilometers away. The system was well known, the warning time measured in years, the collision rehearsed in detail. DART's mission conditions were as optimal as possible. Interstellar objects like 3I/Atlas rewrite those rules entirely. They appear without warning, hurtling at hyperbolic speeds, composed of materials that defy expectation. A fragmented interstellar comet spraying debris through Earth's orbital corridor would stretch the DART model past its breaking point. The principle of kinetic impact is simple: hit early, hit hard, and let velocity change compound over time. But with 3I/Atlas moving over 60 kilometers per second, almost triple the speed of any near-Earth asteroid on record, the required energy skyrockets. The intervention window collapses from years down to weeks, maybe only days. No lead time exists to design or launch a custom impactor. And the intercept itself would demand precision at closing speeds so extreme that even the smallest deviation would result in a miss. At those velocities, planetary defense has no margin for error. The overlooked question is always the same: what happens after impact? The DART mission's success left behind a debris cloud, each fragment spinning off into space on its own path, some traveling even faster than the asteroid itself, in a real-world strike against a fragile, volatile heavy object like 3I/Atlas. The result could be far more chaotic. Instead of a single deflected rock, the outcome might be a spray of unpredictable fragments, each one becoming a new threat. Current deflection models are largely based on solid bodies of rock or metal, not porous shells of frozen carbon dioxide and dust riddled with empty voids. For a nucleus already near structural failure, an impact might not redirect but instead complete the destruction, yielding dozens or even hundreds of uncontrolled projectiles. NASA's Planetary Defense Coordination Office, PDCO, has invested years into refining networked sky scans, cataloging potential hazards, and running scenario drills. But those contingency plans were built on familiar assumptions: objects moving slowly, unknown trajectories, and resident within the solar neighborhood. Interstellar arrivals overturn all those expectations. Their extreme speeds, exotic chemistry, and unpredictable paths stretch existing frameworks to the breaking point. DART proved humanity can shift the orbit of a small asteroid. But it didn't prove readiness for a barrage of interstellar fragments, especially when warning arrives too late for anything beyond desperate measures. The truth is uncomfortable. Our strongest defense tool remains early detection, spotting the anomaly before it erupts into a crisis. Quantum interferometers, advanced sensors, and rapid response algorithms are narrowing the observational blind spots. But the system is not foolproof. Each new visitor stretches the boundary. Every anomaly forces scientists to rewrite parts of the defensive playbook. And the haunting question remains: what happens when the next one leaves no time to react? The answer won't come from simulations alone. It's arriving in the sky, moving too fast for comfortable margins. On July 1st, 2025, the Atlas survey in Chile identified 3I/Atlas, only the third confirmed interstellar body, barreling through the solar system at 61 kilometers per second. Immediate studies using quantum algorithms and atom interferometry revealed its weakness: an extreme 8:1 carbon dioxide to water ratio coupled with a density under 0.4 g/cm superscript 3. This combination pointed to an airy, porous framework prone to collapse. When paired with solar cycle readings showing coronal mass ejections exceeding 1,500 kilometers per second, simulations began forecasting catastrophic outcomes. Solar activity of that magnitude could fragment 3I/Atlas into meteoroid streams comparable to those that once caused orbital failures and widespread power outages on Earth. Yet despite the precision of new measurements, predictive models still leave uncertainties. The timeline of a potential breakup, the scale of fragment dispersion, and the exact orbital paths remain unresolved. Some key results from ongoing monitoring remain restricted to classified channels. What is certain, however, is that interstellar bodies with chemistry and structure similar to 3I/Atlas represent risks that cannot be fully anticipated under current systems. They threaten satellites, electrical infrastructure, aviation navigation, and even planetary defenses designed for slower, more predictable objects. For now, 3I/Atlas stands as both a warning and a revelation. New quantum instruments have uncovered weaknesses invisible to conventional tools, highlighting dangers hidden in plain sight. And just as importantly, it has shaken our confidence in old assumptions about the safety of interstellar travelers.